Итак, здравствуйте, коллеги.
Good afternoon, colleagues. I'm happy to see you. My name is Sergey Khrenov. I work in the company PVS-Studio, and we develop statistic analyzer language for C++, C Sharp, and Java. Today I'll be talking about the quality aspect that has to do with the development of the statistical code analyzer. I'll tell you what it is in detail and the specific side to the development and testing. In other words, I'll tell you how we achieve good quality of our tool from the point of view of the bug finding quality. We'll briefly touch upon the main aspects of testing, of which you probably know very well. I'll concentrate on the approaches and internal tools that we are using in our company in order to make our tool, our statistical analyzer, more better quality. I'll start from the introduction. What is a statistical analysis? Statistical analysis can be understood as an automated code review. We have a classical tool of statistical analysis. We work with the basic code, trying to find some error and bug patterns using different approaches. This way we helping programmers in their work. The statistical analyzer is showing the highlighting for the programmer the suspicious points that the programmer decides whether to fix or not. A big plus of the statistical analyzer is the big high speed of operations. And for dynamic analysis, you only need to run the code. Among the disadvantages are the noise of the statistic analyzer. If you find something using the dynamic analyzer, it's probably 100% error. With the statistical analyzer, you need to decide for yourself. So there's a margin of error. The statistical analysis tools have become more and more popular these days. Briefly, a few words about the comic example. How does the statistical analysis works and how it helps to a developer or a tester? Imagine you have this kind of code. For the code review, you need to find a bug clearly. It's almost impossible, but there is a mistake here, a bug. Here it is, highlighted. The next slide describes what kind of error it is. We can see that after putting this code through the statistical analysis, the tool shows the where the error is, or the bug is, because the programmer used the copy-paste technology. He simply copied the second abbreviation, irrespective of the condition, even though it will not be a critical mistake, just a different color pattern. It's just an illustration. Even such small mistakes lead to major consequences and repercussions. You can see it has a certain number. Basically, analyzer works this way. They analyze the code and give you a warning, and the programmer analyzes the code. This mistake is quite obvious. It's not always possible to see the mistake clearly. What is the problem here? We have a tool, uses standard approaches, and everything will be fine. Unfortunately, this is not always the case. Clearly, the tool is complicated. It uses the sophisticated internal mechanisms. It's not a simple pattern matching analysis of the regular variations to use it to the full degree. You need to compile the code. It's not the analysis of the text file. It's you need to use different programming languages, languages that you explore, that you need to understand quite well, because the analyzer is sometimes written using these languages. To check the C++, the analyzer needs to be written in C++, and the same is true about the C Sharp and others. There are a number of platforms and standards you need to comply with. I mentioned them, CVA mixer, those are industrial standards. It complicates the product, and eventually you see that there's not enough standard methods in order to make the product high quality one. It is, you can and you should use everything you can. You can get hold of. We use the code review, unit tests, and all the possible kinds of testing. But the major problem here is not just the quality of the code, which now is not surprising to anyone. Everyone is used to fast running, good problems, but the quality of the running. For this, we use our proprietary approach. We check our analyzer in real-time project. We download them from the open sources, with the open code for the matching languages, and we check them. This pool of projects is quite large and involves tens of projects. We check them and see how analyzer behaves in this project. This way we try to understand and make a conclusion, decide on the quality. In order to approach the quality, well, I'll describe to you what the analyzer looks like from the side. Since I'm a C# developer, I'll give you example of C#, although C++ and Java also use the similar internals, so this could be a way for you to understand it. Any analyzer must collect some information about the project. This is how it looks like, the project, the solution, in order to make conclusions and try to find a mistake, an error in the code. Let us look at the lower part of the tree and go from bottom to top. The main thing you need to understand is we need to get the syntax tree, the code tree. We need to disassemble our code in order to move around. And secondly, we must know what we have in our tree. We need to possess the information about every node. This is a semantic model. We can see the syntax tree and a semantic model. In order to analyze any document, and under the C# documents, we understand the simple basic code document. We need to apply this information. Documents they make up a project, and projects make up a file. If you work with C# studios, you use the same approach. Important to note here that we see a certain spin-off from the project, so-called the compilation. We need this kind of compilation to get a semantic model. We have a tree and tree nodes, but to understand what kind of information is kept, the variables, constants, what's inside, we need to compile a project in order to solve all the dependencies and the links. This information makes up the compilation information. We use the MS Build Roslyn. It's a solution from Microsoft, which represents all the instruments, the APIs, for you to go inside your code. The Roslyn can create a semantic tree, can compilate. It has its compilators inside. You simply need to use this tool to create your own analytics. Basically, that's it. In brief, this is how the syntax tree looks like, created by Roslyn. We can see that for a simple construct, we see declarator, we have variable x, which is assigned with 1. We see nothing difficult here. We can say root here, and it has a node with a local declarator and variable. It's all subject to disassembly. We can go up in the tree and see what kind of X it is. We can see that it's simply part of the declarator, which is a bigger part of something bigger. And we can see the standard ratios here, like a pattern. we can walk around this tree. Rustling gives us possibilities, methods, and classes for this. Yes, we're moving around the tree, we can move around, trying to understand what's happening. Here at some point, x equals 1. We need to know what is x exactly. The tree doesn't have information about what x is. We turn to the semantic model, I mean the second part, and it instantly gives us information that x means in C sharp. Apart from saying to us that it's x, it says that it's declarator and has the meaning of 1. This is the main elements of the semantic model. We can go up the tree and again find the x and try to see that understand that x equals in, but it doesn't always work this way with the big semantic complication. That's why you need to process the project and get this information. A little bit of code for you. This is how this looks. The synthetic approach. It's actually a workable approach, a real one. How the solution path and the string project path allow you to get different information. For example, you need to create a workspace object. You can see that we can simply get the current solution highlighted by this first square. After we open the solution through the path, and then we can simply get from it the whole list of projects. It's simple, like this. Rosalind gave us a list of objects. They include the project. You can work later with. Depending on what you want to work with, if you look at the last line, you can see they can give you solution, which you can use to find information about all the projects. What we do next? The second option is to receive the project. The same if you know the path to the project. Again, you need to analyze the project, basically do the job to review the files and making trees and receiving values. Here, it's quite simple. Again, we receive the compilation object. We see here that we receive the project's object, and we simply make a review. We hear enumeration of documents in this file. The file is exactly the document. Using the Rosling terminology, we simply review all these basic files, source files. For each, you can get a file. You can get a syntax tree. All the methods are standard. There's no magic here. And again, we use the methodology called visit, which is a key technology of Rosling. We give a certain root, and using this root, it reviews all the nodes of all the children in this tree. It will review all of them and pass by all of it, which means that it will one by one name all the overloaded methods. How does it work? You have a tree and you have blocks E, for, switch, and so on. You can, when you write a diagnostics report, you know what you're doing. For example, you need to check all the ifs. There's a special overload methods called this statement. If you overload these methods and use your implementation method, when you call this visit, you will always get into this. You will receive the code fragments where this if is used. Basically, you will find all the ifs, fors. For each part of the code, there's the overload. This way, you can review the tree. and get into the places that you are particularly interested in. This is how it works. Of course, in reality, it is used differently. And what the Roslin gives you when creating diagnostics, we wrapped it up. But this is the basics. I'll tell you how the diagnostics is created in a nutshell, so for you to understand what the quality here stands for. You can say a simple diagnostics about the true meanings that were omitted. A programmer was writing a code, and after the exception object is created, the throw needs to be used. Instead of writing a throw, new argument, he omitted throw. As a result, the object is created, but created for nothing. It is clearly a mistake. Our analyzer caught this mistake. It has some internal code. And using an example of these diagnostics and everything mentioned above, we need to understand how we can implement this diagnostic. You need to describe for the overload methods that will be defined in our tree, the object creation nodes. They are new. It will review the code, and whenever it comes across new, it will show us the place. When we see that, we need to understand what is being created there. Then we apply logic and check what is created there, the system exception object in this case, and not some other abstract object. As soon as we see that it's a new or some voluntary object is created, we check if it's used at all. It's done in a number of ways. You can go higher and see that this construct is not part of the declarator, is not part of the function guarantee. It is done quite simply. We see that they're not particularly used. We understand that this is an error. An analyzer gives a warning. This way, the diagnostics is created. This is the simplest example. Diagnostics in this case is quite simple, but still it requires a big infrastructure around it. This is how this diagnostics looks like. It's a real part of the diagnostics. I deleted all the unnecessary parts. We created UIs. We wrapped it up with UIs so that work with methods that will give you the fragments in the code. You need to sign up to a certain UI. It's used here on this slide. It's used. We use the visit objects creation expression. The main function here, the visit object creation. This method will be used for every fragment that uses the word new, where we send it ready-made semantic models and additional information of the node. We send the node there that analyzer came across. Then you understand the logic, internal logic of this part of code. The programmer uses the code and replies to 4 different ways of writing the code.
Was there a mistake or not? The same was done in VCSR diagnostics. Prognoser can subscribe to various interfaces depending on what fragments of the code he is searching for. Perhaps he needs to overcome the whole code, then you use a general visitor. There are a lot of additional things and utilized, but diagnostics works like that. Let me tell you a few words about the algorithm of diagnostics development and quality. Before you develop a diagnostics, you need to come up with a fragment of code where the analyzer should work for sure. Why? Because it is easier to work with at the beginning with small synthetic examples because it's easy to write them. Programmer writes down evident fragments of the code where there's no throw or there is a gap in the new, gives it to analyzer. We implement it as unit tests. These are internal synthetic tests. You need them only at the stage of development, as a matter of fact. Then, as soon as you write them, you develop diagnostics for them. And you try to make sure that diagnostics passes the tests. It's a classical TDD. We develop code according to tests, and the system should criticize the right places and not criticize other places. And then we have self-testers. Self-tester, as I told you at the very beginning, is an instrument that takes a pool of projects. It takes an analyzer and starts to check all the projects one by one. And there is a set of logs and reports and draws conclusions. Reports are compared between each other, and then decision is taken what to do next. Usually at this stage, diagnostics behaves improperly because it's raw, and at the very beginning you gave it the synthetic tests, so it's not good. That's why this process can repeat multiple times. Already when you have real projects and you develop your diagnostics till perfection. The main identifier of quality is to minimize the so-called false responses. Usually, statistic analyzers give you some noise. This is how they work. They cannot give you 100% guarantee that there is a mistake because a programmer sometimes doesn't know if it's a mistake or not, even if it's a developer who knows the context of the code. What can we say about an instrument? But a programmer who writes down the diagnostics knows the diagnostics, analyzes the results, and improves it, makes extensions. For example, there are cases when we know the diagnostics criticize something in vain. The fifth step is critical. You need to have a balance between the right and wrong criticism, but the work doesn't start here. From statistical point of view, the improval of diagnostics on the basis of real projects is 70% of all the time of development. In reality, diagnostics can be developed within 2 days. And then it takes about 10 or 12 days to bring it to perfection. Diagnostics is not some kind of a regular figure. It's a real code, several entries and lines of the code. It's not big, but it has extensions. It has some admissions and allowances to have less false launches, false responses. For 10% are related to optimization and 20% account for minimum false responses. So here is how our statistic analysis look like. Now I want to show you how positive and negative tests look like. Positive tests is something which is written at the very beginning. It's some kind of autosynthetics. There are some evident cases, comments, plus V3006. It means that analyzer should give you this warning when it goes through this line. It's the first warning. It's evident. You created in vain. Then, in the second case, you also have created it in vain. And the more strange fragments of code you have, the better it is. But diagnostics is written by a programmer. And even if a programmer is highly qualified, he might not be ready to imagine all this set of constructions. The languages are difficult, there are different options of writing a code. You can see a construction that you might not know. This synthetical tests are good, but you need to use real projects in order to bring the system to perfection. But you cannot survive without synthetics. Was a positive test, that's a negative test. These constructions are evidently correct. Here are exceptions and variables. Then you create an exception and you take it out of the method. It's not a mistake because exception was not created in vain. Here, the situation is vice versa. If an analyzer criticizes something, it means the test is not passed because analyzer should keep silent. Here you can see the filtration of V3006. Negative and positive tests are passed. What about real projects? We use our own self-written instrument. We have to develop self-testers for C, C++, C Sharp, and so on, depending on the project. They are related to our analyzers. You take results and you compare them with the results of the previous test, and you try to draw conclusions about the behavior of the analyzer. It has a lot of requirements. The most important thing is that it should give an opportunity to compare results with the previous results of analysis, and then the programmer can see what has changed. Because he makes changes, writes new diagnostics, improves old diagnostics, creates new constructions of language. And we need to see now how the analyzer behaves after the changes. Also, it needs to be able to set such changes. It needs to be able to say, yes, these changes are correct. When can you need it? You can need it in all the cases where, as I told you, you create a new diagnostic. So when a new diagnostics is created, you check it at the pool of projects and you need to see new reports. If you see the reports and you see that there are no critics, it's bad. Or, for example, you improve the diagnostics and you check the duration of the check and it takes 5 minutes, just as like it was before, and it has to be optimized. Or, for example, you see additionals inside of the analyzers. Some anomalies are expected as new responses. For example, unexpected is that the duration of check increased. It's an anomaly and we didn't expect it. You have different logs and reports. You can compare that. This is how a log looks like. A log is actually a report of our analyzer. It is an XML file where you have information about a mistake. Here I see the information about the mistake and additional data. So let us have a look at a mistake, the code of mistake, where it was found, and other additional information. It's impossible to develop such a report manually because analyzer's report consists of thousands of such fragments. XML can be really huge, that's why we have an instrument that can compare such reports. It works like that. Summarizing everything I told you, you improve diagnostics, or you create a new structure of the language or new diagnostics, or you change the internal mechanisms inside of the analyzer machine. You take a real pool of projects for IC Sharp. It's about 60 projects. You just take the projects, load them from GitHub, and use our analyzer. And then for each iteration, you have a log. You report for each project. It's a report about mistakes, and then you compare it with a report used as a sample. If there are no differences, okay, fine, you can keep going. If there are differences, you need to see what kind of differences there are. If there are no differences, it might be also a reason to think about it. For example, you have created a new diagnostics, but nothing has changed. Then it's a pause for thought. But usually, the absence of differences is fine. If there are differences, you need to understand if it's expected or not. And then, if you understand that the differences in our report are expected, then you make this log a sample log. And then when you check other projects, they will compare the data with this report. If you don't think that the data is correct, you don't set it, the programmer keeps working, improve the diagnostics, check what was wrong, why the duration of the check improved, and so on. Programmer create such self-testing instruments in the form suitable for a programmer. Like here, for example, you can see a checked solution, DEPA, at on the 15th of April 2019. There are differences between the logs. It's a regular HTML report. A programmer can easily find differences and make conclusion. In green, for example, you can see additional in current, which means that there are new responses. There is a mistake V3008. For a programmer, it's a pause for thought. So in this project, there is an abnormality. Then a programmer takes the project, starts it locally, and then checks the analyzer in the studio or other DE for Java, for example, and understands this abnormality and then eliminates it, then checks everything from the very beginning. It's an iteration process. It's never ending because analyzer is being developed all the time. This is how programmer is interacting with such things. I think it's a very useful form. Regular HTML. PVS-Studio self-tester C# analyzer looks like that. Full of projects, 52 projects for now. Okay means that there were no differences identified. Diff means that there is a difference, and you need to draw your attention to it. You need to open logs and reports of the project and understand what's wrong. But about as-built, you see that there is diff and there is slowing down of work, additional 7 minutes. It's an additional pause for thought. The analyzer was additionally working for 7 minutes. It's quite a lot. Must build is a very big project. Nevertheless, this is how the programmer sees it. Then you save this information in the logs. And later on, you can analyze it and draw conclusions about it. And the work doesn't stop when you do it all, even multiple times. Then diagnostics goes to users and to production, and then customers or users start using it in their own project. Our test base becomes even bigger. Our diagnostics and analyzer lives in the real world. And often we receive feedbacks from consumers. On the basis of that, we can introduce some changes as well. The mechanism goes on again, again, and again. We work to improve the quality of our analysis all the time. It can be also related to some internal changes when the standards of the language change. For example, when there are internal mechanisms of analyzers that are being improved. Conclusion. What are the advantages of a good static analyzer? One of the main criterion is speed of work. Statistic analyzer should be quick because after statistic analysis, the companies want to solve problems. Usually the companies have millions of lines of codes and they have problems with it. They don't know what to do with it. To work with it manually is important. Code review doesn't work anymore. A person just cannot survive, and we don't have so many resources. So they come to us for the instrument statistic analysis. Of course, there are a lot of various instruments, and you need to work with all of them if you have an opportunity. If you can use dynamics, use it. If you can use code review, use it. But statistic analyzer helps you resolve some of the problems. If the company is mature enough and understands that it requires the use of statistic analyzer, most probably it has a huge code database, and the analyzer should be able to work quickly, because if the company waits for 4 days till the results of analysis come, it's too long. Minimum of false responses. It's bad if programmers have to go through hundreds of warnings because of one possible mistake. The relation between mistake and false responses will still be there, but you must have less false responses. Mistakes can be also different in terms of their importance. There are critical mistakes. You need to draw your attention to them as soon as possible. Then there's medium-level mistakes and low-level mistakes that you can even mock in the settings. Just noise and waste. Anyway, everything should be there. You need to have as less false responses as possible. I told you about it. Then the development of integration system. Usually, it refers to big companies. If you use statistic analysis on the codes with millions of lines, companies might be afraid. They say if you use statistic analysis, you have tens of thousands of responses, and the company says, what are we going to do with that? Do we have to look through all of them? We have been developing the instruments for 20 years and solve them, but how come can we have so many mistakes? However, it's fine. In case of statistic analysis, the majority of responses are fine, but it doesn't mean that you need to work with that right away. A good instrument allows you to send them into suppress base in the technological depth, and you will start your analysis on the new code. It also should give you an opportunity to come back to the previous code if you have time and resources for that, and improve it if you need it. The essence of statistic analysis is not just to take a project and check it once in half a year, get thousands of responses and analyze them for the next 6 months. That's why we always say that you need to do statistic analysis more often. Yes, you can develop such statistic analysis and apply them in various sectors, but it's better if programmers use such statistic analysis while they are developing programs. Why so? Because they can find mistakes at each stage. Plus, the company needs support. Because if it's an instrument without support, the company is not interested in it. Support is needed when you insert the analyzer, when you make settings. If you have a statistic analyzer and it has all of these features, use it. It's a good one. Thank you. I can answer your questions, dear colleagues. Thank you for your attention. We have just 1 minute for a question. Short question. Anyway, you can come to me in the discussion zone. Sergey, thank you for your presentation. I have a question. If a new analyzer is used for new language, it has passed all the synthetic tests, and you base your project on that, and suddenly you understand that you don't know whether it works correct or not. There's nothing to compare. And the initial stages, there's a programmer who is working. For example, when we introduced Java, we took projects, they were checked by analyzer, and that is really the problem of the first time. when you need to do some deductions. So a person starts working anyway, but as the time goes, analyzer will reach a point when it can use the data from the algorithms. It's not an automatized process. It's a process with the participation of a human being. A person makes changes and is waiting for reaction, waiting for such consequences as false responses, real responses, extended time of response, and so on. Yes, you said that when a new version of the language appears, the analyzer doesn't work. If I have Java 6, for example, but you analyze mistakes written in Java 9, for example. No, it's not like that. We work with a code. We need to support certain versions of languages. However, our analyzer or similar analyzers that use initial code work differently. We are not an antivirus. We are not working with binary code. Yes, of course, if you see construction that we support, like C++, I know that now they have something like C++20, it's a problem. We won't see this mistake, but we are working with initial code. And it gives us an opportunity to outperform, because if we have the standard, it's not so important. If you know that the constructions, if there are such new constructions in Java, for example, we can analyze them. If you speak about binary analysis, we might have problems with them, but hopefully I have answered your question. You know, if we have something old and something new, we can compare it. Please give this prize to the guy who asked me a question. It's a T-shirt. Thank you. All right. Thank you, dear colleagues. I will be happy to answer your questions if you have them. Thank you for listening. Thank you for your attention.